Good morning, students. Today I shall discuss about substitution reaction. What is substitution reaction? A substitution reaction is a type of chemical reaction in which one atom or groups of atoms in a molecule is replaced by another atom or group. There are two types of substitution reaction. One is nucleophile substitution reaction and second one is electrophilic substitution reaction. Now, nucleophilic substitution reaction. Here the attacking agent is a nucleophile. Suppose an alkyl halide is a substrate and it is treated with a nucleophile. Then RNU is the product and this X minus is the leaving group. Next, electrophilic substitution reaction. In case of electrophilic substitution reaction, electrophile is the attacking agent. Suppose an example of benzene, this is a benzene and this hydrogen is replaced by this bromine atom. So when this benzene is treated with bromine with FeBr3, then hydrogen is replaced by an electrophile Br plus and bromobenzene will form. So this is an electrophilic substitution reaction. Next, the basic idea about nucleophiles and electrophiles. What are nucleophiles? Nucleophiles are basically electron-rich species. They can donate electron pairs to the electron-deficient species. And electrophiles are electron-deficient species. Electron-deficient species means lack of electrons. So, they attack the electron-rich centers or the sites where the electron density is maximum. So there are different types of nucleophiles and electrophiles. Some examples of nucleophiles like charged nucleophiles, that means Cl minus, Br minus, I minus, etc. So they are electron-rich system. And neutral nucleophile means ammonia, water, etc. In case of ammonia, nitrogen has lone pairs, so it can easily donate electron. Similarly, in case of water, oxygen has lone pair, so it can easily donate this lone pair. Now, nucleophile with partial negative charge, RMGX, where R minus is the nucleophile. Alkyl lithium, where alkyl this R minus is the nucleophile. Similarly, some examples of electrophiles are Cl plus, Br plus, I plus. So all the electron deficient elements are electrophiles. Some neutral electrophiles are SO3, CH3Cl, etc. Types of SN reaction, that means type of nucleophilic substitution reaction. Number 1, nucleophilic substitution unimolecular, and number 2, nucleophilic substitution bimolecular. Next, nucleophilic substitution unimolecular. It is an example of alkyl halide, and this X, that means halogen, this X is actually a leaving group. So when this leaving group is removed from the reaction medium, then a carbocation will form. This is the carbocation, and this is a planar system, and the carbon of this carbocation is sp2 hybridized. So this is a planar system. So when nucleophile attacks, nucleophile may attack from this side and also may attack from this side. So if the nucleophile attacks from the same side of the leaving group, then it will the retention of configuration like that. And if the nucleophile attacks from the opposite of the leaving group, then it is the inversion of configuration. So in this reaction, after completion of the reaction, 50% mixture will be inversion configuration and 50% product will be in retention of configuration. So the total is overall decimalization. So this is basically a two-step reaction. First step is formation of carbocation and second step is attacks of nucleophiles. In the rate equation, you can see here in the rate equation of this reaction, rate is equal to rate constant and concentration of alkyl halide. So this is a two-step reaction. So first step is the slowest step, and the first step is known as RDS, rate determining step. So in case of rate determining step, the there is no nucleophile. So in the slowest step or rate determining step, if we say the rate equation, there is rate equal to K into concentration of Rx, because in the rate determining step there is no nucleophile. That's why it is called unimolecular substitution reaction. Next, factors affecting SN1 reaction rate. First point is stability of carbocations. As you have seen that in the first step there was the formation of carbocation. Leaving group is removed from the uh, substrate. So the formation of carbocation. So our first step is formation of carbocation, and the carbocation, if the carbocation is 3-degree carbocation, then it is more stabilized than 2-degree carbocation, than primary carbocation. So 3-degree carbocation or tertiary carbocation is most stable than 2-degree carbocation, than primary carbocation, because of inductive effect and hyperconjugation effect. Second point is effect of leaving group. If the size of the leaving group is more, it can easily removed from the substrate. So if the leaving group is iodine, then it will be easily removed from the substrate. So the effect of leaving group, that means if the size of the leaving group is large, then it can be easily removed. The third point is effect of solvent. Polar solvents are favored in this reaction because there is a formation of carbocation. So carbocation can be stabilized in polar solvent. So polar protic solvent are the best suited for the SN1 reaction. You can see that in ethanol medium, ethanol water mixture medium, if there is 40% water plus 60% ethanol, it is so in case of 100% ethanol, the reaction rate is less than 40% water plus 60% ethanol, and it is less than from 80% water to 20% ethanol than water. That means here dielectric constant increases here, so the reaction is favored in case of polar protic solvent. Next, nucleophilic substitution bimolecular reaction. Suppose an example, alkyl halide CH3Br, it reacts with OH minus ion, and this Br is substituted by OH. So the formation of alcohol. Now in SN2 reaction, that means substitution nucleophilic bimolecular reaction, here the nucleophile attacks the carbon and the leaving group removes from the reaction medium, and both the situation will happen simultaneously. This is pentavalent carbon. In the transition state, this pentavalent carbon appears, and then formation of alcohol. Sometimes this is known as umbrella flipping, or the stereochemistry is inversion of configuration. This is one step reaction. In the previous slide, you have seen that in case of SN1 reaction, this is two-step reaction, but in case of SN2 reaction, it is single step reaction. And in the rate equation, the rate is equal to rate constant into concentration of alkyl halide into concentration of nucleophile. So this is bimolecular reaction. Next, factors affecting SN2 reaction. First one, substrate. SN2 reaction rate decreases as the steric hindrance increases. Why? In case of alkyl halide, Here, suppose instead of this hydrogen, if there are some bulky groups, then it will be difficult for a nucleophile to approach the carbon center. So, with increasing steric hindrance, the probability of SN2 reaction decreases. Here you can see the steric hindrance increases. Steric hindrance increases here. So, the rate of reaction decreases. Here are some examples. Here Cn minus is nucleophile and it can replace the bromine atom. Now, if suppose CH3Br. So, in case of this reaction, the relative rate is almost 1000. So, with increasing the bulkiness of this alkyl group, the rate of the reaction gradually decreases. Rate of SN2 reaction gradually decreases because it is very difficult for a nucleophile to approach from this side, that means back side of the nucleophile. So with increasing steric hindrance or with increasing the bulkiness of alkyl group, the rate of SN2 reaction decreases. Then second point, leaving group. Better the leaving group, faster will be the rate of SN2 reaction, like SN1 reaction. Third point, nucleophile. Better the nucleophile, higher will be the reaction rate. Suppose HS minus, RS minus, these are the good nucleophiles. Then ammonia, chloride, these are the moderate, and water, ROH, that means alcohol, carboxylic acid, they are the weak, nucleophiles. There is some comparison between SN1 and SN2 reaction. First point, rate law. This is unimolecular reaction and SN2 is bimolecular reaction. Big barrier. Carbocation stability is very important here because the first step of the SN1 reaction is formation of carbocation. In case of SN2 reaction, steric hindrance of the alkyl group is very important because if the steric hindrance is large, that means if the alkyl group has bulky size, then it is very difficult for a nucleophile to approach the carbon center. Next, alkyl halide. 3-degree alkyl halide is better than 2-degree than 1-degree because there is formation of carbocation, and 3-degree carbocation is more stable than 2-degree and 1-degree. And the opposite phenomenon is observed in case of SN2 reaction. Nucleophile, generally weak nucleophile, and in case of SN2 reaction, strong nucleophile is important. Solvent, in case of SN1 reaction, polar protic solvent is very important, and in case of SN2 reaction, we need polar aprotic solvent. If I use polar protic solvent, then it will form hydrogen bond with the nucleophile. So nucleophile becomes so large, so the attacking power will be less due to bulkiness. That means the rate of nucleophilic reaction will be less. And stereochemistry, in case of SN1 reaction, the first step is formation of carbocation. So nucleophile can attack from both the side, so racemization occurs. But in case of SN2 reaction, nucleophile only attacks the opposite side of the leaving group, so that only inversion can occur. Next is electrophilic substitution reaction. Electrophile means, as I have already said, that electrophile means electron deficient system. So in case of electrophilic substitution reaction, some electron rich system will attack these electrophiles. In this example, there is a benzene ring and these pi electrons are loosely bounded, so they can easily attack this electrophile, and the hydrogen present here is replaced by this E. This is the electrophilic substitution reaction. And the mechanism, this pi electron will attack this electrophile and form this carbon E bond, and there will be the positive charge, and this positive charge will move through resonance. So this carbocation is very much stable due to resonance. Then the base will attack this proton and the substituted product will form. So this is our electrophilic substitution reaction. There are so many electrophilic substitution reaction. First one is Friedel-Crafts reaction. Friedel-Crafts reactions are two types. One is alkylation and another one is acylation. In case of alkylation reaction, the benzene ring is treated with alkyl halide and a Lewis acid, AlCl3. Aluminium chloride acts as Lewis acid. So from benzene, alkyl benzene will form. Here are some more examples. Benzene to ethyl benzene. This Lewis acid, aluminium chloride, is very important here because this aluminium chloride will form AlCl4 minus, and this part is our electrophile. CCH3 whole 3 plus. So the positive charge on carbon atom, this is the electron deficient species, so it is our electrophile. So to form the electrophile, this Lewis acid is very important. Next is acylation reaction, Friedel-Crafts acylation reaction. Like alkylation reaction, here is reagent is RCOCl. RCOCl in presence of anhydrous AlCl3. So here C double bond OR will form, ketone will form, and here also this Lewis acid will form AlCl4 minus and generation of this RCO plus, that means electrophile. This electrophile will substitute this hydrogen and the ketone will form. Next, halogenation reaction. Benzene is treated with halogen with anhydrous FeX3, that means Lewis acid. Then electrophile Br plus will form, and this Br plus will replace this hydrogen of the benzene and halobenzene will form. Nitration reaction. Benzene is treated with concentrated sulfuric acid as well as nitric acid, and nitrobenzene will form. Here the electrophile is nitronium ion, NO2 plus. This HNO3 reacts with sulfuric acid and it will form NO2 plus. This NO2 plus acts as electrophile, and in that way this benzene is hydrogen of this benzene is replaced with this nitronium electrophile. So this is an example of electrophilic substitution reaction. Then sulfonation reaction. In case of sulfonation reaction, benzene is treated with SO3, sulfur trioxide, and sulfuric acid. This sulfuric acid reacts with sulfur trioxide and it will form SO3H plus, which is our electrophile. This electrophile replaces this hydrogen of benzene and it will form benzene sulfonic acid. This is also an important example of electrophilic substitution reaction. So this is about our electrophilic substitution reaction and nucleophilic substitution reaction. So thank you everyone.